have the EasyChat server loaded up in Immunity Debugger. I have it running. We can see that it's running down here in the bottom right. In order to exploit this program, we found a exploit here on the internet at exploit.db.com. So this is the exploit. This is what it looks like. It's written in Ruby. Well, we're going to write ours in Python. So basically, we look at this code. Looks like they're importing some libraries. Got some variables going on. They got the shell code. They got their buffer. Basically, the only thing about this code you really need is this URL right here, because they're exploiting the URL function. So we'll just copy this and go to our box here. We can start a new file called exploit py python, of course. Actually, we don't need system, we need socket. This argv command is just basically letting us put an IP address as an argument. And we're going to use port 80, being that our chat program uses port 80. We're going to build our buffer. We're going to use 2000 A's. And we need to send this buffer. And then close the socket. Well, from earlier, I told you that we only needed that URL. This is the URL. They're putting the buffer in the username variable and the buffer in the password variable. Well, we don't have to use the buffer in each variable. We only need one. So what we can do is we can just remove this one, and we can put in a variable of our own. We'll just call it test. I want to split this up into two parts. So I'm going to copy this and then delete all of this. Don't need it right here anyways. And in this part of the buffer we don't need. We do, however, need the get command. We're going to put that in a variable called buffer2. And then the other part of that URL is going to go down here. So like before, it said that the buffer is going to be here, so our buffer is here, and then underneath it we're going to append the other part of the URL, which I think is still there. So then we have that. We have to append the buffer. So then we have that. Alright. Not quite done yet. We need something here on the end of this. And the reason why we need something on the end of this is because if we look at a GET request from a packet here, if I get the right window, here's a GET request for another Python script over the internet. If we look at the actual GET request, it says GET space /. That's going to be common in all GETs. Well, at the end here, they got a space and then HTTP /1.1 \r\n. So let's add that to our program too. Then we'll take a look at the GET request again, and we notice that there's some header information here. We don't care about the header information, but we do care about these last carriage return and last new line character. We have to add that to our GET request, otherwise it won't work. So we got to add that in here. So then this part is correct. We have our GET /, which is correct, and then we have our URL that we're building, which is, we got that off of this. So then we're connecting to the IP address over port 80. We're getting a URL from the program, or actually we're going to send it. So we're going to ask for some information, and then we're going to send the buffer, and then we're going to close it. So let me save this. See if it's saved. And then obviously it doesn't have the right permissions. So all it has is user read write permissions. The group permissions, it only has read, and then the other permissions is just read also. So let's give it some execute permissions. Now it should be green in our list, so now we can execute it. And the argument that I made for it was the IP address of the system we're attacking, which is, come on, this address here. So we can send that exploit. Look at our program. We got an access violation when reading 41, 41, 41, 41, which is all A's according to the ASCII table, which we can see right here. Oh, there we go. So what did that do? Well, it didn't overwrite EIP. It just threw an access violation, which means that it went into what's called a SEH exception. So if we look at the SEH chain, this is what's there right now. Well, SEH are records that have two parts. The first part is a pointer to the next SEH record below it, and then that one has a pointer to the next SEH record below it, and then so on. Well, the second part of it is the SE handler. Well, this handler has a function that has 4 arguments that are sent to it. So basically it returns 4 arguments. Well, this is what the stack will look like once you're inside this function. It will have a return, and then you'll have your 4 arguments that were loaded on the stack. Well, we're interested in the establisher frame, and with the establisher frame it actually gets the same address of the top record, so it's a pointer to the next SEH record, which is below it, as you can see right here. So if this establisher frame points to the top of the record, we can actually tell it to jump over the handler and into whatever code we want. And we do this by using what's called a pop-pop return sequence. So basically we're going to go into the SE handler. So the stack's going to look like this. We're going to pop the first value off the stack, which is the return. We're going to pop the next value, which is the exception record, and then we're going to return the establisher frame. Well, when we return the establisher frame, we're going to use a short jump, which is represented by EB, and then the next byte tells it how many bytes to jump. Well, the reason we're going to use 6 is because we're going to have to jump over the NOP we have to put in there for padding, and the other NOP we have to put in there for padding. So there's 2 bytes right there. And then the address right here is going to be 4 bytes. So we have to jump those 4 bytes. So 4, 5, 6. So that's why we're jumping 6 bytes. And that's going to allow us to jump to our shellcode. So in order to find the SE handler, the establisher frame address, what we can do is we can actually throw an exception to this chat program here by starting another program that runs on the same port number, which will throw an exception. So you can't have 2 programs listening on the same port. So what we'll do is we'll open up Easy Chat in the debugger here with this other program running on port 80. We'll have to press play. When it goes into the main part of the program, it's going to throw an exception. Well, if we look at the SEH chain, we have the kernel on the bottom, which is the OS, SEH record, which is shown here. OS HEH records on the bottom, and then all the other records get built on top of it. So this record is built on top of this record, on top of this record, on top of this record, and then on top of the OS record. So let's look at the top record, follow it in the stack. Well, this stack is not the exception dispatcher stack yet, because we're not inside the SE handler yet. So let's go inside the SE handler. Well, in order to go inside the SE handler, we have to look at it from a disassembler in the CPU window here. We have to breakpoint it. Being that this thing's paused and it threw an exception, we have to press Shift F7 to give control to the program, immunity debugger, and then press F9 or press the play button here. And then we'll break inside the SE handler function. So now our stack should look like this. We should have a return, exception record, and the establisher frame. So let's take a look at that. So it says the return is what we want. This one right here is the exception record. This one right here is our establisher frame. This next one is the context record, and this next one is the dispatcher context. Well, we're only interested in the establisher frame, which is 1, 2, 3. So we go 1, 2, 3, this right here. So this 0, 1, 2, 2 FC97, which if we copy that, put it in Notepad here. This address should match the top of our SEH chain, which was a DLL file that started with an A. I can't remember what it was. Let's take a look. No, it started with an R. That's right. I was wrong. So 10122FC9C. So let's take a look at our notepad here. 0122FC9C. I actually told you the stack address, sorry. This is the address it's going to return to right here. So you see that they're the same. So it's going to return to the top record. So what we can do is we need to find a pop return sequence, because like I told you before, we have to pop this off, we have to pop that off, and then we have to return. Well, we need to find this sequence. Well, in order to find this sequence, we have to look through the program itself and all the dependency DLLs, because we have to look for, we actually have to look for an address that will work for our exploit. The address can't have any nulls in it. So once you have the program running again, we can use a plugin called PVE find address. We need to look for no safe SEH DLL files within the program that are dependencies. Look at the log, tells us what DLL files we can use. We need a DLL memory page that has no zeros in it. So this top one starts at 1 and then ends in this number. This one starts at this number, ends at this number. This one starts at this number, ends at this number. Everything in between, we can't use this one or this one. So everything in between here are not going to have any nulls in it somewhere in the address in this DLL. So we can look for that DLL in the executable modules. Here we can find a sequence of commands find pop pop return, just like in our presentation here. We're going to pop this off, and return the establisher frame to the next record, which will be our jump 6 bytes, and then that will jump to our shellcode. So I found pop pop return in this DLL that doesn't have safe SEH enabled on it. This has got zeros in the address, so we can't use this virtual address. We have to find a different one. We do that by Control L. I just hold it down. I just watch the addresses till they change. So I'm just watching for 00 change. When it does, I lift up. We'll copy this first address here. You have to put it in a different form so the computer can understand it. They call it Little Indian, but really, if you were to look up what Little Indian and Big Indian is, we're actually changing it to Big Indian, but you know, whatever. Everybody has their different view on it, I guess. And the reason why I think it's Big Indian is because E5 is bigger than 10. So technically this form would be Big Indian. But the computer will read this in as Little Indian. So that's why they call it Little Indian form. This is being read in to the computer as this address, which is Little Indian, being that it starts with 10. So it's this number is littler than this number, so they call it Little Indian. But technically you change it into Big Indian, so we have to change it into Big Indian for the computer to read it right. So we have our pop pop return address now. We go back to our program here. We're going to change this up a little bit. The reason why we're going to change it up is because I had a few problems earlier, so I had to redo the video. So let's try redoing it. Within this address here, we're going to do the jump. This will overwrite our record, our pointer to our next record. And this one is just what we just figured out. We're going to comment these out yet because we don't know. We don't know where in memory the next pointer is or the handler. So we're actually going to find out where it's at by using Metasploit. So we do that by using pattern create. I'm going to create a 2000 pattern. Oh, forgot the Ruby extension. There's our pattern. Put it in our program. Can't remember the address of this box. So we sent our stuff. A pattern got recognized because it's the access violation with a bunch of gibberish here as far as numbers. Let's look at the SEH record. Follow up the stack, see which one. Okay, so now we found the characters that it overwrote, so now we need the offset of them. We can do that with another program called pattern offset. Let's look at the numbers, letters. AH2A. AH2A. So it's 216. Well, we know that it's 216 characters to this point, and the next 4 bytes. 216 characters to this point. The next 4 bytes is this one. The next 4 bytes is this one. Okay, cool. So go back to our program here. Don't need this anymore. We're going to do the 216 A's. We're going to go into our jump. We're going to go into our pop-pop return sequence. And then we're going to add our payload. Well, the payload is built with Metasploit 2. Find the payload you want to use, doesn't matter what it is. When you find it, just save it, because we're going to have to do something else. We have to think about this real quick. What are we doing? We're sending a URL. So we can't use all of the characters in our payload because the URL address space, this address space doesn't recognize all the characters. So what characters can we use? I'll let you think about that for a minute. This website tells you what characters could be used. In this table, all these characters can be used in that URL. But all these characters right here can't be, because 00 through 1F were designed to be control hardware devices. Control characters have nothing to do inside a URL, so all of these characters can't be used. So we have to put all these characters in Notepad. Okay, once we enter these characters in a Notepad, this is what you're going to come up with. 00, we have to put the \x in front of all the numbers instead of the percent sign. Well, this is the function that we're going to use. MSF payload. With our payload, we're going to have to use an argument called exitfunc equals SEH. With an argument R, pipe it to MSF encode, tell it that it's an 86 architecture, and tell it all the delimited characters, and then make it C code. We have to use this, otherwise it won't work. There's our shell code. You can highlight it, copy it. The top here tells us that it's an alpha mixed encode with 746 bytes for the size. So we can go put this in our shell code spot. We have to make sure that there's parentheses around the shell code. So let's go up here, put the other parenthesis on. We can save it. And the reason why we go 216 characters, and then we go our jump, and then we go our pop return sequence, and then our shell code is because that is what we have to do. This is the sequence we have to recreate. We have to recreate the jump, the pop return sequence, and then we have the shell code. So let's save this and then send it to our program. See what we get. We got to restart it, of course. Press play. It's running. Send it. We're getting an access violation, which is what we want because we have it in a debugger. If it wasn't a debugger, we wouldn't get that access violation. So we got to do Shift F7 and press play. So it's running. Let's see if we have a shell. Remember that exploit was 44444. There you go. Got a shell. Now you can do whatever you want. You can navigate to the C drive, Windows System 32, and you can list everything. You can add files. You can do whatever you want. I'll leave that exercise up to you when you get that far.